As I have told you in the previous theory, it is necessary to solve any kind of differential equation for knowing the value of q. Now, first of all, I am starting this analysis by writing the differential equation of the charge deposited on the capacitor is given by Vm by L cos omega t is equals to d square q by dt square plus r by L dq by dt plus q by L c. So this was our differential equation. Now this equation can be modified in this way. See, I am taking the left hand side as it is. I am making just few changes. So this is di by dt plus r over L. This is the value of I. Now, what is this charge actually? This charge is the integral of electric current passing for the particular time interval. So, here 1 upon LC will be as it is into the integration I dt, where here I is the electric current and dt is the time interval. The solution of the above equation means this equation can be obtained by using complex number. So do you know what is complex number? Complex number is the combination of one real number and one imaginary number. So here the solution is in terms of a complex number. It is of the form z is equals to x plus iy, where here I is an imaginary number. Now, in order to find out the actual answer, we have to convert these quantities into the complex form. So, the complex form of cos omega t means with respect to I, now I have to write. So, e raised to I omega t and the value of electric current I in the complex form, that is small I. So, with the changes, now I can write down this equation in the form of, therefore Vm by capital L e raised to I omega t, that is equals to d small I by dt plus r by L into small I plus 1 over LC integration I dt, and this is equation number 1. And with this, the real numbers and complex number I am differentiating or separating. So here Vm, it is the maximum value of voltage, so this is real number. L is the value of inductor, that is also a real number. Here current I is in complex number. E raised to I omega t is also in the complex form. The value of this resistance is also a real number, and the value of this capacitance are also in the form of capacitance, means real number. Now, the solution of this equation 1 is given by one relation I is equals to Im, that means maximum current, into e raised to I omega t. So this is my equation number 2. So whenever you find this kind of differential equation, then it is not necessary that you integrate all the sides and then find out which is answer. But you can directly write down this solution. I is equals to Im e raised to I omega t. And now to check whether this solution is correct or not, the values which are coming in the differential equation means di by dt, integration I dt, and then we can check the left hand side is equal to the right hand side. So let's find out first of all this di by dt, and therefore from equation 2, di by dt is equals to d by dt Im e raised to j omega t. Now here I have used j because instead of I, because we have used the I for one purpose that we cannot use for another purpose. And so you correct equation 2 by putting j instead of I. Now this Im is constant, so I am taking it outside of the integration. The differentiation of e raised to j omega t is like this: j omega e raised to j omega t. So this is the value of di by dt. That is equation number 3. Now if you integrate I with respect to time, then what you will get? So from equation 3, now I can write down di is equals to Im j omega e raised to j omega t into dt. And now you integrate both the sides. Then again the same relation will come. I is equals to Im. This j omega will be constant. So e raised to j omega t divided by j omega. So this will be cancelled, and now you are finally ended with this equation. And so integration I dt is equals to Im integration e raised to j omega t into dt. And now I am substituting all these values in equation number 1. So I will get on the left hand side, so that will be as it is. Vm by L e raised to, and now the cos omega t, what I have considered as e raised to I omega t, that you also considered as e raised to j omega t, and the right hand side will be Im j omega e raised to j omega t plus r by L I e raised to j omega t plus 1 over LC Im e raised to j omega t divided by j omega. So this is actually the answer of Vm by L e raised to j omega t. More simplifying this equation, so we'll end with the answer in this way. From the left hand side, I am taking Im as common. So from the first value, I will get j omega. In the second equation, I will get r over L as common. And in the third step, I will get 1 over j omega LC and you can check the printing mistake in your textbook, that is on equation number 2.3.5, in which in the numerator this j omega will not come and the right hand side will be Vm over L. So you can check from both the sides, e raised to j omega t is cancelled out. Now what I am doing, I am multiplying both the sides by capital L. Therefore, Im into j omega L plus R, this L will be cancelled out, minus 1 upon omega C. Now see here why I have written minus 1. Actually it is minus j, but the value of 1 upon j I am writing over here. This 1 upon j can I write in this form, j over j square, and the value of square of any imaginary number is minus 1, so that is minus j. And so I am writing over here minus j over omega c, and this L is cancelled out. That is equal to Vm. And now I have the value of the current which is passing through the components of the circuit, and that is actually the maximum value. So Vm divided by j omega L plus R minus j over omega C, and this is your equation number 5, and this is shows the relation between the complex current I and the complex voltage Vm into e to power j omega t. If we substitute this value of equation number 5 in the solution that was of the type I is equals to Im e to power j omega t, therefore I is equals to Vm e to power j omega t divided by j omega L plus R minus j upon omega c, and hence this relation is very similar to the Ohm's law. I is equals to V by R form. And now if you want to find out the two quantities which are arriving in the solution, that are j omega L. So here the frequency is included, inductance is included, and the both quantities are multiplying with one imaginary number, and this quantity is known as inductive resistance. Also, if you find out another quantity that is of the form minus j over omega c, this is called the capacitive resistance or reactance. And this reactance is always of the capacitor C, and we can use this symbol ZL and ZC for denoting them. Therefore ZL is equals to j omega L and ZC is equals to minus j over omega c. Now these are actually the values, but their magnitudes we can find out by XL and XC. So what is XL actually? The XL is having the value ZL divided by J. So it is omega L. and the value of Xc is Zc over minus J, and so the value of Xc is 1 upon omega C, that is obtained from the relation Zc over minus J. And here the summation of the ZL, Zc and the resistance itself is called the impedance of the system, or we can say the impedance of the series LCR AC circuit. So Z is equal to ZL plus ZC plus the resistance itself. Here the value of R I am putting as it is, plus J into omega L minus 1 upon omega C. And now the equation for complex current small I can write down as Vm e raised to j omega t. And if you remember the numerator of equation number 5 or equation number 6 actually, I have not written that number, but that was the solution of complex current small I, and that is of the form like this: R plus j omega L minus j over omega C. So this is simplified in this way. So here comes the voltage divided by impedance, and that is I am giving equation number 6 at present. This equation is the Ohm's law with the complex current I, this complex voltage and also the impedance. And here if you see the equation of impedance where complex quantity is arising, so this Z is also considered as complex. So now you have studied one more symbol today, that is of impedance, and that is denoted by capital Z. If you take the value of capital Z in terms of magnitude and direction, e raised to j delta, and so this is just the supposed value, and now I can substitute equation number 7 into 6. Therefore, I is equals to Vm e raised to j omega t divided by mod Z e raised to j delta. Here the exponential terms are coming, so let me take it on one side. So Vm upon mod Z e raised to j omega t minus delta. And we know we can expand this exponential term into the cosine function and sine function by this relation. E raised to ix is given by cos x plus I sin x. So here I will expand this equation also in this way. So it is Vm upon mod Z. Here you don't confuse, this V are always in small manner, not in capital manner. You can write in the capital manner, but here we have considered by the starting that the voltage V is equal to small Vm. So here I am writing all in the small letters. So the equation will be cos omega t minus delta plus, here instead of I we have the value of j sin omega t minus delta. Therefore, the complex current I, now I can write down in terms of some real values and some imaginary values. But first of all, the value of mod z I can write down in terms of r square plus omega L minus 1 upon omega c whole square and its under root. So this is the magnitude what we have found out by the point difference property. Now I am writing my capital current I, which is actually flowing through the circuit. So that is the real part of I, and the real part is related with the cosine value only. So that is equal to Vm cos omega t minus delta divided by the mod z, and here mod z is under root r square plus omega L minus 1 upon omega c whole square. And see, here I have not considered this imaginary term because I only interested to find out the value of real part of I. Now if you see, the current and voltage changes into the time period. So such kind of graph is given by this figure. So here voltage and current are shown, and the difference between the legs in their phase behind the voltage and current is delta. So delta is actually the phase difference between voltage V and current I. Now this equation is showing the complex impedance of the circuit, means Z is equals to R plus j omega L minus j over omega C. We have seen earlier about the real part only, but the real part of the complex number is only R, and the imaginary part of Z is given by the graph which is shown in this figure, where from the point H, which is showing the complex number Z, is obtained. So distance OH is equals to Z. Also the impedance Z is given by the equation ZL plus ZC plus R. And now from this figure my task is to obtain about the value of mod Z. So here I am consider the values which are given. OD is equals to R. The value of OA, that is omega L, and here is the imaginary axis. So such kind of arrangement you have to remember on the real part as well as the imaginary part. And this is very easy because you just have to consider the actual values on the real axis and the imaginary axis. The value of OF in the negative direction of vertical type, that is 1 over omega C, and from which I can find out the value of OG, means this value, that is omega L minus 1 upon omega C. That is actually the imaginary part of Z, and it is written in this symbol. IM stands for imaginary and Z is for impedance. And if we want to find out the total part of OH, then OH is equals to OG plus GH, that is equals to the value of GH is R plus omega L minus 1 over omega C. And now we have the value of OH, that is equals to Z, and from the law of Pythagoras, the value of mod Z I can find out from Pythagoras theorem. mod z is equals to under root of OD square plus dh square. And here we are applying the Pythagoras theorem to triangle HOD, that is equal to under root of the value of OD square is r square plus the value of dh square, that is omega L minus 1 over omega c whole square. And if you want to find out the phase difference, then you have one equation in terms of the slope form, that is tan delta is equals to HD over OD, means two arms of the triangle, that is equals to omega L minus 1 over omega c. This whole term is divided by the resistance. And so with such kind of equation or geometrical representation, we can obtain the value of z, which we have determined theoretically. So this question is also can be asked in two partitions. The first partition is you find out the solution and show the current voltage characteristic with respect to time, and the other one is to find out the value of impedance and the phase difference by the help of the geometrical representation. Now we will see some different cases of AC circuit.